Let's look at it, almost because different.
Okay, let me get to that first. I'll come.
Take it back. Oh. Yeah. Okay. That's very. These all can be the same version. Oh. Christine, yeah, as long as they got. Yeah, you can provide anything to project. Yeah, yeah, there was that's very. Oh, wait, I didn't even go.
I mean, as long as you get it goal. Oh. The fact that you try again, if it doesn't, so if you want to apply the. Getting that one file. So the thing is, never find it is something that, the way it looks at colors. Right. So actually, I don't think that they define that. What you want to take, but outside. All of them. You want to accept. Generally, when they leave stuff. Yeah, so for the report, I would like a separate table. That's a good point. So one thing people did last year a lot was they just took a screenshot of the answers table. I mean, you should see this report as kind of like a professional level report. And so, it's gonna look a lot cleaner if you just make your own table. Plus the answers table has a lot of extra information. So for our purposes, the main things that you need are just the Young's modulus, the Poisson's ratio, and maybe the density if you're adding a gravity. So. Yeah, I would prefer you make your own team. All right, it's 5:30. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Good to hear. All right, so before we start today, I have kind of a funny story to tell. I didn't tell it in my last class because there's a lot of people in the last class that was in the class yet my class yesterday, so I didn't want to have them hear the same story. But this has nothing to do with finite elements, by the way. This is a funny story. So I visited my parents on Tuesday night. It was nice. I should really see my parents more often. So I was watching TV with my dad. And so there's in case you haven't heard, there's an election coming up. So there's a lot of political ads being run right now. And so kind of the meta or kind of the trend for political ads nowadays is not really to say good things about yourself, but to say bad things about your opponent. So there is a congressional race in Orange County. So there's I think she's the incumbent. Her name is Michelle Steele. And so she is going against someone named Derek Tran. So they're fighting for a seat in the House of Representatives. So this was a commercial for Michelle Steele, and then the punchline for her commercial is "Don't trust Tran." And my last name is also Tran, so it's me and my dad looked at the TV, was what the hell, Michelle? Like, what did we do to you, man? Um, and then my dad's like, she can't say that. That's your cousin. So I asked my dad, like, am I really related to Derek Tran? He's like, I don't know, maybe. I mean, a lot of Trans are related to each other, so I don't think he's my cousin, but you never know. But yeah, a little bit of a funny story to start today. Okay, so back to finite elements. So today's another lecture day, so nothing too exciting. But we're going to continue on with our lecture notes on truss elements. So today we're really going to dive into the 2D stuff. So we're going to see how our truss elements kind of expand to 2D situations and how that changes our element stiffness matrix. Okay. So we started a little bit of that at the end of class on Tuesday, and so we're going to basically kind of continue with that derivation, and then hopefully do an example today as well. Okay. All right. So the only announcement I have is that has to do with the only assignment that's active right now for the class, which is the midterm project. Okay, so just a reminder, the midterm project is due next week, actually due 1 week from now. So make sure that you guys are working on it. I've gotten a lot more questions over the last couple of days, so that's good. But if you haven't started it, please make sure that you do, because there's even though the simulations may seem straightforward, but there's going to be questions that come up in terms of how you're setting things up, whether what you're thinking of constitutes as separate loading scenarios. What are some good material properties, formatting for the report. Make sure you start soon, just because I expect next week's gonna be pretty busy in my office hours. So you want to start sooner to kind of get your questions answered sooner. Okay. All right. Any questions I can answer before we get started for today? Okay. All right. So let's go ahead and pick up where we left off. Okay, so just to kind of recap, I'm going to scroll up to the lecture notes that we did last time. So you don't have to write this down again. We talked about this on Tuesday. Okay. Okay. So what we were discussing at the end of Tuesday was, what if we want to take our knowledge or our technique for direct stiffness method and apply it to 2D situations. Okay. And by 2D, what I mean is, situations where our truss elements and spring elements, can be angled with respect to the horizontal. Okay. Because so far we've only done problems where the truss and springs are all parallel to each other and they're all facing the same direction. Okay. But if we were to tilt one of these elements upwards, how can we solve that situation? Okay. Okay. So I introduced this concept of a reference coordinate system and a local coordinate system. So a reference coordinate system is kind of our standard XY coordinate system, where X is perfectly horizontal, Y is perfectly vertical. Okay. When you have a coordinate system like this, you can take any vector and define its position and define its direction using the components of that vector. Okay. So what we have right here, this UX, UY, these are the components of vector U. Okay. So that's a pretty common way to describe, a vector in 2 dimensions and 3 dimensions too. You can get up to that point too. Okay. Right. And so those two components, we kind of said was basically our vector projected onto the reference axis. So our vector we project onto the x-axis, that gives us ux. We take our vector, we project it onto the y-axis, that gives us uy. Okay. And most importantly, if you have the components of your vector, you can write it in this kind of vector notation, right? And so you can say that our vector u is equal to its x component multiplied by a unit vector I hat plus uy plus a unit vector j hat, okay? Where I hat and j hat are unit vectors that are in the same directions as your coordinate system, okay? Okay, so you can take that exact same vector and you can define its components with respect to a different coordinate system, okay? So it's the same vector. So u has not changed from the top figure to the bottom figure. It's still the same. The only thing that's changing is how we describe it. Okay. And so if we take a new coordinate system, and specifically we take a coordinate system that's slightly rotated compared to its the previous one. Okay. Projecting this vector onto these new coordinate systems are going to give us new components. Okay. So I called these ux hat and uy hat. And then, if we put this in vector form, we get ux hat times I hat underline plus uy hat plus j hat underline. Okay. And kind of the final idea that I left you guys with on Tuesday was that even though these are 2 different descriptions, they're the same vector. Right? So it's basically just looking at the same thing from a different perspective. Okay. Or calling the same person by a different name. Right. So just calling Billy, Bobby, or Bill, Bob. Somebody, that's the only name I can think of in my head right now. But so if these 2 vectors are the same, then what we can say is that the first description, which is ux times I hat plus uy times j hat, is equal to our second description, which is ux hat plus times I hat underline plus uy hat times j hat underline. Okay. Now this is going to be kind of the starting point for our discussion today. Okay. So let's go ahead and start our notes for today. So this is truss elements in 2D. Okay. All right. So remember, we can describe the same vector in different ways depending on the coordinate system. Okay. But a description is just a description. So the vector itself is not really changing. Okay. Okay. So just to kind of, let me bring down that equation from above there. We have ux times I hat plus uy times j hat is equal to ux hat times I hat underline plus uy hat times j hat underline. Okay. On the left-hand side right here, we have the description of our vector in the reference coordinate system. And on the right here, we have the description of the same vector, but in the local coordinate system. Okay. So ideally what we would want, based on this equation right here, we want to be able to form a relationship, between the different components in the different systems. Okay? Okay. Because if we can do that, if we can form an algebraic relationship between the components in the two systems, then that's going to be kind of our building block for our 2D trusses. Okay. So how are we going to do this? How are we going to form this relationship between those two systems? So where we're going to start here is we're going to relate the unit vectors in each of the systems. Okay. Because what we know, so if we compare I hat and J hat versus I hat underline and J hat underline, we know that these unit vectors are parallel to the reference, or excuse me, they're parallel to the axes in their respective systems. Okay. And if we know that in the local coordinate system, the local coordinate system is just a simple rotation of our original reference system, then we can use geometry and trigonometry to relate these unit vectors. Okay. So let's go ahead and do that. All right. So first one I'm going to start with is I hat. Okay. So we know I hat is a unit vector in the reference x direction. So it's a perfectly horizontal vector. Okay. So what I want to do here is I want to form a triangle, okay? A right triangle, where this I hat vector is the hypotenuse. Okay. All right. So how am I going to do that? So let me draw a vector in this direction. Okay. And then to complete the triangle, I'm going to draw another vector that's perpendicular to that line that intersects with our original I hat vector. Okay. So I have a right angle right there. Okay. So the main angle that we're going to be looking at here is this angle here. Okay. So the angle on the left side of the triangle we're going to define as theta. Okay. And we're going to define it in such a way that this angle here is the exact same angle that we need to rotate to get into the local coordinate system. Okay. So this theta right here, same angle as local coordinates, or saying local coordinate rotation. Okay, so just to kind of refresh your memory, let's kind of scroll back up here. Okay. And so if we look at our two coordinate systems here. So if we look at the bottom figure, you can see that the way we obtain the bottom figure is just rotating counterclockwise by an amount theta. Okay, so we rotated the x-axis counterclockwise by an amount theta, and we rotate the y-axis counterclockwise by an amount theta. Okay, so that theta there is the same theta. Okay. Okay. And so what we can do is we can relate the lengths of these two legs of the triangle. So let me call this A vector, and we'll call this B vector. Okay. Let's express the lengths of A and B using our hypotenuse I. Okay. Okay. So first, let's start with the length of the A vector. Okay. So the length of the A vector, if we know the angle And we know the hypotenuse in this case. So we know the hypotenuse is I hat. Okay. We're going to have I hat multiplied by cosine of theta. Okay. And then B, okay. If we use trigonometry one more time, we can say this is equal to I hat multiplied by sine theta. Okay. All right. So that's just using kind of the definitions of sine and cosine, right? So cosine is the ratio of the length of the adjacent side divided by the hypotenuse, and sine theta is the ratio of the opposite side divided by the hypotenuse, right? Okay, we can simplify these expressions because what do we know about the length of the I hat vector, right? The I hat vector is a unit vector. And so unit vectors always have length of 1. And so in these expressions, we can simplify, we can basically get rid of the magnitude of I hat and just say that their magnitude is just 1. Okay. So the length of the A vector here is just cosine theta, and the length of the B vector here is just sine theta. Okay. Okay. Now there's one other thing that we can express here. Okay. And that's the directions of the A and B vector. Okay, so let's start with the A vector. So if we look at this A vector, relative to the I hat vector here, it's rotated, its direction is rotated counterclockwise by an amount theta. Okay. So there's another vector here that is parallel to this actually, so it's the same direction. Okay. And that direction is I hat underline. Where I hat underline, remember, is the unit vector in the local x direction. Okay, so I drew this triangle kind of explicitly so that our vectors are parallel to that. Okay, similarly, B the B vector here is in the same direction as another vector that we've already kind of talked about, and that's the J hat underline direction. Okay, because we know the B vector here is perpendicular to the A vector, and since B is perpendicular to the A vector, it must also be perpendicular to the local x direction. And another vector that's perpendicular to the local x direction is the local y direction. Okay. One caveat here, though, is that because the B vector here is pointing down, it's actually in the reverse direction. So the B vector here is in the same direction as J, just reverse. Okay. So we can use these facts, right? So a vector is defined by its magnitude and direction. So we have both quantities here. So for both the A vector and the B vector, we know its magnitude. Okay, we got that through trigonometry, and we know its direction based on how we drew it. Okay, so we can make an expression for I hat in terms of the unit vectors in the local system. Okay, so in terms of I hat underline and J hat underline. Okay, so let's use all this information here. So from this we can say the I hat vector is equal to the sum of the A vector and the B vector. Okay. And so if we plug in for the A vector and B vector, what we get is I hat's equal to A, which is cosine of theta, times I hat underline, okay, minus sine theta times J hat underline. All right, so this is really cool. So what we can do is we can take this expression here and plug it back in to our equality relationship above. Okay. And so that equality relationship, just to kind of jog your memory, is this one right here. Okay. So what we did was we found an expression for I hat. Okay. And so we can plug in for that one based on the expression that we have there. Okay. So we would effectively eliminate I hat from this expression, and we're going to put everything in terms of I hat underline and J hat underline. Okay. We're going to do the exact same thing for J hat here. Okay. And so we're going to use kind of geometry and trigonometry to find an expression for J hat that we can plug into this equation. Okay. All right. Any questions on how we got this expression here, or kind of where we're going? Okay, good. Okay, so let's do the same thing for J hat. So I'm going to go ahead and draw the J hat vector just like I did up there. Okay. Then I'm going to break this up into two components. One component that's parallel to the local y direction, and one component that's parallel to the local x direction. Okay. Okay, so it's going to look like this. So this angle here is theta. This angle here is 90 degrees. So this is our new A vector and our new B vector. Okay. And this vertical one here, that is our hypotenuse. And so that is our new J hat vector. Okay. Okay, so I'm going to go pretty quickly on this one just because we did this before. So the magnitudes of the A vector in this case is going to be magnitude of J hat multiplied by sine theta. Okay. And magnitude of the B vector here is going to be equal to magnitude of the J hat times cosine theta. Okay. And we know that A vector here is in the same direction. So we can say it's parallel to I hat underline. And the B vector here is parallel to J hat underline. Okay. Okay, so we can use these results here to get an expression for J hat. And so what we can say is J hat's equal to, let's see, sine theta times I hat underline plus cosine theta times J hat underline. All right. So now that we have our two expressions here, let's go ahead and plug those back in. So I'm going to plug in both our expressions for I hat and J hat back into our original equality relationship. Okay. And so if we do that, we get ux multiplied by cosine theta I hat underline minus sine theta J hat underline, okay, plus uy times J hat. So that's sine theta I hat underline plus cosine theta J hat underline. Okay. That's equal to ux hat I hat underline plus uy hat J hat underline. Okay. Okay. So let's clean this up a little bit. So let's go ahead and rearrange the terms. Okay. So I'm going to group together all the I hat underlined terms, and I'm going to group together all the J hat underlined terms. Okay. And so if we do that, what we get is UX cosine theta minus sine, or excuse me, minus UY, sorry, I'm all jumbled up. Skipped ahead. Okay, first expression here is UX cosine theta plus UY sine theta times I hat underline plus minus UX sine theta plus UY cosine theta J hat underline is equal to UX hat I hat underline plus UY hat J hat underline. Okay. So I grouped all the terms on the left-hand side by, whether they're multiplied by I hat underline or J hat underline. Okay. And so by grouping these terms, what we can do now is we can relate the left-hand side of this equation to the right-hand side, okay? Because if you look at the right-hand side of this equation, we also have a term that's multiplied by I hat underline and another term that's multiplied by J hat underline, okay? So what we can say is that these terms must be equal to each other, okay? Because they're both multiplied by I hat underline. And then these terms must be equal to each other as well, because they're multiplied by J hat underline, okay? And so if we write these out as algebraic expressions, what we get is UX cosine theta plus UY sine theta is equal to UX hat, and then minus UX sine theta plus UY cosine theta is equal to UY hat, okay? So those are the two equations that we can solve for here that relate, UX and UY to UX hat and UY, okay? We can even take this one step further. We can put this in matrix form. Okay? Because one way that you can interpret these equations is that they represent a system of two equations and two unknowns, okay? And so what we get from this is cosine theta, sine theta, minus sine theta, cosine theta, multiplied by the vector ux, uy is equal to ux hat, uy hat. Any questions on this? Any questions in the back? I hear kind of a lot of whispering back there. You guys good? Okay, so this system here is quite special, right? So this matrix here, this matrix here is not an element stiffness matrix, but we call this matrix a transformation matrix. Okay. The reason we call it a transformation matrix is that it allows us to transform, you can think of ux and uy, right? Ux and uy here represent coordinates in the reference coordinates. Okay. And so with this transformation matrix, we can take any set of coordinates in the reference system, and so a reference system is a standard X, standard Y, and if we multiply it by this matrix, then we can get the corresponding coordinates in the local coordinate system. Okay. So we call it a transformation matrix because it allows us to transform from one coordinate system to the next. Okay. So transformation matrices are they're not unique to finite elements, and you might have seen them in a previous class, maybe in kinematics or maybe in your dynamics course. But this is kind of just a refresher on what it is here. Okay. So we're going to be using this transformation matrix a lot. So to kind of save myself and save your guys' sanity on writing, I'm going to use kind of an abridged version of this. Okay. And so instead of writing cosine theta, sine theta all the time, I'm just going to use C and S. Okay. Okay. And so if you see that matrix there, you see C and you see S. C stands for cosine theta, S stands for sine. Okay. That's just kind of a shorthand just to kind of make things a little bit easier to write. Okay. Okay. So let's use this transformation matrix to, transform our element stiffness matrix. Okay. Because remember, our element stiffness matrix traditionally is only defined in the local coordinate system. Okay. So our element stiffness matrix for we're gonna do it for a truss. But the same methodology can apply for for a spring as well. Okay. We have F1 hat, F2 hat is equal to AE over L times 1 minus 1 minus 1 and 1. Okay. And then this is D1 hat, D2 hat. Okay. Okay. For F1, F2, D1, D2, those are the nodal forces and nodal deformations in the local coordinate system. Okay. Or in other words, a system that's a coordinate system that's local to the element's orientation. Okay. So we want to use our transformation matrix to transform this into the reference coordinate system. Okay. All right. So first thing we have to do is we have to first kind of expand these vectors and expand this matrix here. Okay. So this D1, so I'll take D1 for as an example. D1 is the axial deformation of the truss within the same direction of the truss itself. Okay. So in this case, any perpendicular deformation is not accounted for in this thing. Okay. So it's a little bit confusing here because you might see F1, F2 here, right? You might think F1 and F2 here are components of the same vector. Okay. They're not. So, don't be confused with kind of what's up here. So, up here, our UX and UY are components of the same vector here, okay? This F1, F2, and by the same token, D1, D2, these are different vectors. So they're not components of the same vector. Okay. So actually, let me kind of draw it out just to kind of illustrate it for you. Okay. And so for a truss element that's in its own local coordinate system, okay. So let's say that we have an element that's oriented like this. It's rotated upwards by an amount theta. Okay. The F1 vector is a vector that's operating on the left node of this truss. Okay. The F2 vector is a separate vector entirely. It's a vector that's operating on the other one. Okay. So in order to use our transformation matrix, we first need to expand all of the vectors here into their separate components. Okay. And so what we basically have to do is we say that we have an F1 x vector that's pointing in the same direction as the element, but there's also going to be an F1 y vector that's perpendicular to it. Okay. Same thing with the other side. So we have an F2x and an F2y. Okay. Now, we're going to assume that they're zero just because of how a truss kind of behaves, but we have to include them anyway, just in order to use our transformation matrix. Okay. Okay. So this is going to expand our element stiffness matrix. Okay. Our expanded element stiffness matrix is going to look like this. And so instead of being a 2x2 system, we are now going to have a 4x4 system. So it's going to be much bigger than it was before. Okay. So we have F1x hat, F1y hat, F2x hat, F2y hat. Okay. This is equal to AE over L. Okay. Now, this is probably the trickiest part here. So we have to expand the matrix itself, right? So we're adding actually two entire rows and two entire columns. But just because we expanded this matrix, it still has to be mathematically equivalent to our previous one, our original 2x2. Okay. And so if we were to perform the matrix multiplication of this matrix multiplied by the deformation vector, we should still get the same equations. Okay. And so that means we're actually going to fill this matrix with a bunch of zeros. Okay. And so we have 1, 0, minus 1, 0. And then the second row is going to be all zeros. Third row is going to be minus 1, 0, 1, 0. And then 0, 0, 0, 0. Okay. And there's D1x hat, D1y hat, D2x hat, D2y hat. Okay, good. So now we're in a better position to apply our transformation matrix, okay? Because if you see, so I'm going to go ahead and circle the pairs, okay? Everything that I'm circling here is a paired set of coordinates in the local system, okay? And so we can use our transformation matrix to transform each of those components into their respective forms in the reference coordinate system. Okay. All right, so I'm gonna do just kind of one vector at a time here, okay? So let's look at the entire F vector here, okay? And so if we write out the pair of transformations here, we have F1 x hat, F2, F1 y hat, excuse me. Okay. This is equal to cosine, sine, minus sine, cosine, okay? Multiplied by its same components, but in the reference system. So this is a regular F1x, F1y, okay? And then similarly for node 2. So node 2, we're going to have F2x hat, F2y hat is equal to cosine, sine, minus sine, cosine, multiplied by F1, or excuse me, F2x and F2y. Okay. Okay. So that looks good. Okay. Now we kind of need to combine these into kind of one system, because the way that we formatted our element stiffness matrix is we have, you know, node 1 stuff on top of node 2 stuff. So let's combine this into one. Okay. So the vector that we're trying to replace here is F1x hat, F1y hat, F2x hat, F2y hat. Okay. So we need to input those transformation matrices there into kind of an appropriate location. And so we're going to have kind of a bigger transformation matrix here. Okay. And it's going to be multiplied by kind of the same components in the reference system. So this will be F1x, F1y, F2x, F2y. Okay. Okay. So once again, you know, same thing that we did for the when we expanded our element stiffness matrix, we're going to basically augment this with a bunch of zeros just to make sure the equations still work out correctly. Okay. And so we have CS minus SC and then 0, 0, 0, 0. Okay. And then on the bottom half, we have 0, 0, 0, 0, and then CS minus SC. Okay. Okay. All right, any questions on how we got this and how we kind of filled this, or kind of the reasons why we kind of filled this with zeros here? All right, so if you kind of multiply this out, you'll see that, you know, this section multiplied by this one, right, will give us basically these two here, okay? And then this matrix multiplied by this vector will give us this one right here, okay? I just kind of filled in the zeros just to make sure that our equations are kind of still consistent. So this is really good. So what we have right here is we have a way through our transformation matrix to transform our kind of our stacked vector into the reference coordinate system. Okay. So we can use this matrix here to perform our transformations, and we're actually going to do it twice. And so we need to apply this transformation to our local forces vector, which is kind of exactly what we have here. And we're going to perform this transformation on our local deformations vector as well. Okay. Okay. All right, so let's go ahead and do just that. Okay, so let me scroll back up here just to kind of remind you of the system that we're trying to replace. Okay. Okay, so I guess I didn't have to scroll up that far. Okay, so remember what we have kind of in the middle of the screen here, this is our element stiffness matrix in the local system. Okay, we have two local vectors here. We have the force vector on the left-hand side, and then we have our deformations vector on the right-hand side right here. Okay, so let's apply our transformation to both of these vectors here to transform them into their local system components, or their reference system components. I'm sorry. Okay, so let's go and do that. And so on the left-hand side with the forces vector, we have cosine, sine, minus sine, cosine, times 0, 0, 0, 0, and 0, 0, 0, 0, cosine, sine, minus sine, cosine. Okay. So we performed a transformation, so now these components are going to be in the reference system. So this is f1x, f1y, f2x, f2y. Okay, no more hats. Okay, let's multiply this by our element stiffness matrix. So that's AE over L multiplied by 1, 0, minus 1, 0, 0, 0, 0, 0, minus 1, 0, 1, 0, 0, 0, 0, 0. Okay. Then we're going to multiply this by our local deformation vector, which we're again going to transform. Okay. And so we apply that same transformation matrix we have, cosine, sine, minus sine, cosine, 0, 0, 0, 0, and 0, 0, 0, 0, cosine, sine, minus sine, cosine, multiplied by d1x, d1y, d2x, d2y. Okay. Right. A lot of matrices today. All right, so just to kind of, put this into context, kind of where we were, okay? Remember this guy, this used to be our local forces vector, so this used to be our force vector with all the hats on it. Okay? And this guy used to be our local deformations vector. And then the matrix that kind of stayed the same is just our element stiffness matrix. Okay. All right, so the last step in this derivation is just to simplify this, as much as possible. Okay. So what we're going to do to simplify it is we're going to take this matrix. Okay. It's kind of an eyesore on the left-hand side there. And so we're going to multiply its inverse by both sides. So we're effectively going to move it to this side of the equation. Okay. And then we're going to perform all the matrix multiplications of the transformation matrices multiplied by the element stiffness matrix multiplied by another transformation matrix. Okay. So we're going to combine all matrices into one on the right-hand side. Okay. By doing lots of matrix multiplication. Okay. All right. So we're not going to do the matrix multiplication. It's possible if you're into that stuff, but I'm I'm of the attitude of we ain't got time for that, so I'm just going to kind of skip to the results here. Okay, so if you do all that matrix multiplication, you do the inversing, and you kind of do it all, you end up with the following result here. Okay. Okay, so what you end up with is f1x, f1y, f2x, f2y. Okay. That's now isolated on its own because we multiply by the inverse. Okay. This is equal to AE over L, okay, multiplied by the matrix cosine squared times cosine sine minus cosine squared minus cosine sine. Okay. And then we have cosine sine minus sine squared minus cosine sine minus sine squared. Okay. Minus cosine squared minus cosine sine, cosine squared, cosine sine. Okay. Then in the last row, what we have is a minus cosine sine minus sine squared, cosine sine, and sine squared. Okay. And this is multiplied by d1x, d1y, d2x, d2y. Okay. Where that matrix in the middle, this is now our element stiffness matrix for our truss, where the truss is angled, with respect to the horizontal. Let me just kind of put a big circle around this guy. Okay. So that was a very, very long derivation, but hopefully it kind of all makes sense. Okay. So when you have truss elements in 2 dimensions, you have to take its angle orientation into account. And it's not that the angle orientation changes its stiffness properties. It's still going to have the same Young's modulus and length and cross-sectional area. The only thing that changes is how we describe its deformation. And so because we have to describe it in this reference coordinate system, then we have to take its orientation into account. So that's why we have all these cosines and sines in our element stiffness matrix. Okay. All right. Any questions on how we got to this point here? Okay. All right, so we're going to start an example. I don't know if we're going to finish the example, just because we have only 20 minutes left. But whatever we don't finish, we'll pick it up on Tuesday. Okay. Okay. Oops. Okay, so this will be our first example in 2D with 2D elements here. Okay. All right, so we have an assembly here. So we have 3 elements. Okay, so we have one vertical element here. That's just like that. We'll call that element A. Okay. We have one horizontal member like this. Okay. We'll call that element C. And then we have one angled member, which is actually going to be a spring, which we'll call element B. Okay. We have a 3-member assembly here, so 2 trusses and 1 spring. Okay. Let's go ahead and label the nodes. And so the node at the bottom here is going to be node 1. Okay. The node at the top is going to be node 2. The diagonal node that's attached to the spring, that's going to be node 3. And then the last node here that's connected to the horizontal truss is going to be node 4. Okay. So we have 3 elements and 4 nodes. We have 1 force that's being applied here. So we have a downward force of 10,000 pounds. And that's going to be applied at node 1. And the other thing we know is that the angle between element B and element C is 45 degrees. And the angle between element B and element A is also 45 degrees. Okay. So the angle between element A and element C is a perfect 90 degrees. Okay. Okay, so let's look at the properties of these elements. So the Young's modulus, so this is going to apply to elements A and C, is going to be 30 times 10 to the 6 psi. Okay. Its cross-sectional area is going to be 2-inch square. And its length is going to be 10 feet. Okay. And again, these are the properties for elements A and C. For element B is a spring. And so its spring constant is going to be 250,000 pound per inch. Okay. Okay. So based on this figure here, based on these properties, what we want to do is we want to compute the deformation of node 1. Okay. So node 2, 3, and 4 are actually all going to be just fixed to the wall. So they're actually not going to participate in the system at all. The only node here that's going to move is 1. Okay. We're going to compute. Okay. We're going to compute the deformation of node 1. Okay. Okay. Any questions on this? Okay. All right. So let's get started. So this is our first 2D problem. So on first blush, it might be a little bit intimidating, but we're going to solve this exactly the same way as our 1D problems. The only thing that's going to change here is that we're going to use a 2D element stiffness matrix. Okay. But our process is still the same. So we're going to first start with the element stiffness matrices for each element. Okay. And then we'll go from there. Okay. So let's start with element A. Okay. So element A is a truss element. Okay. So that means we're going to need to multiply or compute its effective stiffness. So if we take the Young's modulus multiplied by the area, divide by its length, what we get is 5 times 10 to the 5th pounds per inch. Okay. You want to be careful with the length here. So the length in the problem is actually given to you in feet. And so you want to make sure you convert it to inches before you actually compute this factor. Okay. Okay. The other thing, so now that we're in 2D, we have to be a lot more cognizant of the orientation of these elements as well. Okay. So in addition to any kind of property calculations that you need, you also need to compute the angle of the element itself, or in other words, the orientation. And the way that we define orientation is we're going to define orientation relative to the reference x direction. Okay. And so in other words, if you were to rotate from the positive x, the x-axis to the current orientation, how much do you have to rotate to get to that? Okay. Okay, so let's look at element A. So element A here is a vertical element. Okay. And so if we were to start from the positive x-axis, okay, in order to rotate into the orientation for A, we have to rotate counterclockwise by an amount of 90 degrees. Okay. So that means the angle for element A here is 90 degrees. Okay. Okay, so let's plug these quantities in to compute its element stiffness matrix. Okay. And remember, the other thing we have to keep in mind with the element stiffness matrix is which nodes are attached to this element. Okay. Okay, so element A connected to nodes 1 and 2. Okay. And so our element stiffness matrix is going to be F1x, F1y, F2x, F2y. Okay. So let's go ahead and plug into our element stiffness matrix here. So we're going to compute a lot of sines and cosines. Okay. If you want to make things a little bit easier for yourself, you can kind of pre-compute the sines and cosines. Okay. And so for instance, our angle here is 90 degrees. So cosine of 90 degrees we know is 0. And sine of 90 degrees is 1. Okay. So let's go ahead and plug that in. Our element stiffness matrix is AE over L multiplied by cosine squared, cosine sine, minus cosine squared, minus cosine sine. Okay. I'll give you a really pro tip here, just to kind of save you just a little bit of work when computing these. Okay. These element stiffness matrices are completely symmetrical. And so what that means is that if you cut the matrix in half, like a grilled cheese sandwich, basically the matrix is going to have the same components above the diagonal compared to below. Okay, so that the slice there is almost like a mirror. Okay. And so actually, the form of this element stiffness matrix that I typically use actually only contains that upper slice. Okay. Okay. So when I compute these element stiffness matrices, I only manually compute just whatever is above that slice right there. Okay. And then what I do from there is I take my results and then reflect it down to the bottom half. Okay. Okay, so let me show you. So for this first column, right? So for a matrix that's symmetric, a symmetric matrix is basically equal to its transpose. And so basically what you can do is you can take this result, rotate it down in there. For this minus cosine squared, this is going to come right here. And this minus cosine sine is going to come into right there. Okay. So you're taking the first row in your matrix and you're kind of writing that into the first column. Okay, so the first row becomes the first column, second row becomes the second column, third row becomes the third column, and the last row is already filled by that. Okay, so let me show you what I typically do. So I typically have this matrix in this form. Okay, and I compute this matrix kind of one row at a time. And as I fill the rows in, then I fill in the corresponding column as well. Okay. So let me just write in this this deformation vector here. Okay, so let's go ahead and start plugging in. So we know AE over L is 5 times 10 to the 5th. Okay, so that's going to be a factor that is outside. Okay, so let me compute the first row in this matrix here. Okay. Okay, so I know from this angle here that the cosine of this angle is 0 and the sine of the angle is 1. So any quantity that involves cosine, I know that it's just going to be 0. Okay. Okay. So first we have cosine squared, so that's going to be 0 squared. Next we have cosine times sine, so that's 0 times 1. Minus cosine squared, so that's minus 0 squared. And then minus cosine sine, that's minus 0 times 1. Okay. So of course, all of those are 0, but I just wanted to kind of plug it in just to kind of show you. Okay. All right. So now that we've written the first row, I'm going to take all those entries in the first row and then rotate them downwards into the first column. Okay. Okay. So for instance, this one's going to come here. Okay. This one's going to come here. And then this one, which is the last entry in the first row, is going to become the last entry in the first column. Okay. So that's how you can save yourself a little bit of work. And so, just write the top half and then just rotate it down into the bottom half. Okay. Okay. Let's do the second row now. So the second row starts with sine squared. So sine squared is going to be 1 squared. Then we have minus cosine sine, so minus 0 times 1. And then minus sine squared, so minus 1 squared. Okay. All right, so once again, I'm going to write these down into the columns. We have a minus 0 times 1. And then a minus 1 squared that goes in the bottom of the second column. Okay. Next, we have cosine squared on the next row. So that's going to be 0 squared, and then cosine times sine. So that's 0 times 1. Okay. We only have one term to rotate down here. So that's this one. That's 0 times 1. Okay. All right. And then the last entry here is just sine squared. And so that's just going to be 1 squared. Okay. So definitely make use of that trick. Definitely make use of the fact that your stiffness matrix here is symmetrical. It's going to save you a lot of work. Okay. Sometimes you don't really think about, you're going from a 2x2 element stiffness matrix to a 4x4. 4x4 matrix means that there's 16 things that you have to compute. And so if you can cut that down, help you cut down on some mistakes too. And so, because anytime you're punching in a bunch of numbers to a calculator, it's human mistakes, human error is bound to occur. You want to cut down on that as much as possible. Okay. Okay, and so if we perform all this arithmetic, we get 5 times 10 to the 5th multiplied by 0, 0, 0, 0, and then 0, 0, 0, 1, 0, minus 1, 0, 0, 0, minus 1, 0, 1. Okay. d1x, d1y, d2x, d2y. Okay. This is equal to f1x, f1y, f2x, f2y. All right. So that's the element stiffness matrix for element A. Okay. All right. If you're lucky, a lot of your elements will have angles of either 0 degrees or 90 degrees or some permutation of that, maybe 180 or 270. And so your element stiffness matrix ends up pretty simple. So there's a lot of zeros here, which is nice. But sometimes, your element stiffness matrix is not nice like this. And so, we have to do a bit more calculations. Okay. All right. Any questions on how we got this result here? Okay, so the next element stiffness matrix for element B is going to take a while, so I don't want to start that now in the last 5 minutes. So we'll pick up this example again first thing on Tuesday. So thank you guys for coming today. Hope you guys have a good rest of your day. Make sure you guys are starting your projects. Ask me questions, tomorrow, ask me questions Monday, Tuesday, Wednesday. I'll try to be available as much as I can, just so that there's kind of no issues before the submission. Okay. All right, so thank you guys for coming today. Hope you guys have a good rest of your day, and I will see you on Tuesday. Yes, I'll be available over email as well. So yeah, please, you can send me an email. If it's something quick, then I think email probably would be the easiest thing, but I'll also be available over office hours next week as well. Yep. Oh, yeah. So that was just the so instead of writing cosine theta, sine theta, um, I just have this instead. So C is the same thing as cosine theta, S is the same thing as sine. Yep.
I didn't finish equaling this part.
Oh, yeah. So all I did there was I just added these extra perpendicular vectors. So F1 y hats in that direction, F2 y hats in that direction. Mhm. Is that yeah? Sure.
So, first question, the loading scenarios, can they all be the same since I'm testing which material?
So
better for the objective?
So I would like for one loading scenario to be change, like maybe change the direction. Because if you have all the loading scenarios, you just change the material, you'll have the same forces, the same direction. All of your results are going to look the same. Now the numbers will change, of course.
Yeah.
But then, the color distribution is going to be all the same. So I would prefer to have at least kind of two different situations where maybe take the force that was maybe originally in this direction, maybe it's like in this direction instead, or maybe it's like in that direction.
Okay.
Or maybe you change the constraints up a little bit, actually, one person had a really good idea with the handle. What if you have kind of a defective handle where instead of being bolted in two places, maybe you have it only bolted in one.
Okay.
And you have just one fixed support. So what's going to happen then if you apply force this way, this ends up come up.
Okay.
That's going to be a very different result than if you have bolted in two sides.
Okay. And we have one more question. Oh, for the material properties, what would you like us to list for our materials, like the yield strength?
So yeah, yield strength would be good. I mean, at the very least, I want Young's modulus and Poisson's ratio. Those are going to be probably the most relevant ones. If you're testing for failure, then yield strength definitely would be good to list as well. Also, yeah, someone asked this beginning of class 2. So in the report, I asked you to make like a table of the material properties.
Yeah.
So I would like, so remember this report's kind of supposed to be kind of a professional report.
Yeah.
And so what a lot of people do is they just take a screenshot of the.
I was just gonna make my own table.
Yeah, just make your own.
Yeah.
It's a lot of. Yeah.
Probably.
Yeah.
It's trying to look for that. And for one of section, it says list 8 keywords.
Yeah, don't worry about that.
Okay. Yeah, I was like, what did I do?
That template is just a generic template for just scientific papers in general.
Okay.
And so, if you're curious, so if you write kind of a paper and you publish it kind of in the wild, you put those are basically hot keywords.
That are commonly used.
Exactly.
Okay.
But for you guys, you guys are all, it should be like finite elements, structural, ANSYS, stuff like that. But, yeah, don't worry.
Okay. Okay. Should be my question. Because my objective, I think I told you, the Hercules hold.
Yep.
So one condition, or one of the loads just change the forces and just describe, how that can be an objective.
Yep.
Okay, like say, for example, like the stresses the forces in the Y affect the handle in this situation. Okay. I like it present.
Yep.
I don't know if I'm thinking too complicated for my fixed support.
Yeah.
I chose a bolt.
Okay.
Calculated the three of those.
Okay.
It's too complicated or?
So that would be if you want to do a Finite simulation on the bolt itself. So the preload would kind of mostly affect that. So for this case, we're not simulating the bolt, we're simulating the part. The pre-stress is not gonna make that big of an impact on the.
Okay, so I can just put on fixable.
Exactly, yeah.
Okay.
Yeah, in reality, pre-stress, it does make a big difference.
Yeah, that's.
Yeah, but for this one, this is a pretty simple simulation, so, yeah, we're not.
Okay.